We've computed a few second-order derivatives by now, not only in these videos, but hopefully you've tried out a few yourself. One thing that you may have noticed is that oftentimes there's a lot of redundancy. Some of the derivatives end up being the same. Is that a coincidence? And if you haven't noticed it, let's do a quick example to point it out. Here is a function of 3 variables. Let's compute some second-order derivatives. Of course, we have to start with the first-order derivatives, which we can compute as follows. You may want to pause at this point and try it yourself, just to get in the extra practice. Now, we're not worried about the pure derivatives, but instead, let's compute the mixed derivatives. For example, the x derivative of the die sub yf isn't too bad to compute, giving us 1 over y plus z squared. But here's the thing. If we differentiate die sub xf with respect to y, then we get exactly the same result. Or, if we differentiate die sub z with respect to x, and you can probably guess that the z derivative of die sub x is exactly the same. And just to cover all the bases, I'll write down the yz derivatives as well, but of course, we expect them to be the same. If you look at these, it's probably not too hard to see what the pattern is. It seems as though the order in which we apply the derivatives does not matter. Does this turn out to always be true? Effectively, yes, especially for us, and we owe this to a theorem by a fellow named Clairut. Suppose then that f is a function of n variables and a is some point in Rn. If we choose 2 different variables, which I'll indicate by I and j like so, and the second-order derivatives with respect to x sub I and x sub j both exist and are continuous at a, then they're equal. This is exactly the theorem that we want. It says that xy and yx derivatives are the same, or xz and zx, or whatever combination of the things that you like. And it's going to save us a lot of time, since it significantly reduces the number of derivatives that we have to compute. In the example above, I was able to compute these 6 mixed partial derivatives just by doing 3 computations. Of course, I'd still need to compute the 3 pure partials, xx, yy, and zz, but 6 computations total is a lot better than the 9 that we otherwise would have had to do. Here's a super cool fact. Clairut generalizes to more than just the second-order derivatives. It turns out that the only thing that matters is how many times each variable appears in the differentiation. To give you an example of what I mean by that, let f be a function of 3 variables, and let's look at a very particular 4th-order derivative. The xxyz derivative is the same as the xyzx derivative, is the same as the yxxz derivative, etc., etc. You get the idea. Anything with 2 x's, a y, and a z are all going to be the same. In fact, there's 12 of these things, so if we had to compute the 4th derivatives, it saves us a lot of work. Thus, Clairut's theorem gives us a slight improvement to the total number of higher-order derivatives that we have to compute.